Okay, so we're going to talk about vector spaces. So what is a vector space? It's basically the space where vectors live. Now remember, when you study real numbers, you study general properties that are satisfied by all real numbers. And the set of all real numbers can be thought of as a space where real numbers live. So in the same way, you have to define a space where vectors live. And you characterize this space by certain properties. So we're going to talk about these properties. So definition examples. Okay, so a vector space over the real numbers consists of a set V, which is the set of vectors, along with two operations: addition, that's addition of vectors, and multiplication, that's scalar multiplication. Now these are the properties that these operations must satisfy. The set of vectors is closed under vector addition. In other words, the sum of any two vectors is a vector. Of course, you can compare that to real numbers. The sum of any two real numbers is a real number. So it's kind of a similar property. Vector addition is commutative. It doesn't matter which order you add vectors. And if you remember how vectors are often added head to tail, you can draw this picture. Suppose I add this vector to this vector. Oops, why is it not working for me? Let's try it again. Suppose I add this vector to this vector, and you add them head to tail like that. Now, and the resulting vector will be here. The arrow that goes to this point, from this point, so that's the resulting vector. Now, if this was my V and this was my W, notice that if I had done W first, let me see if I can actually rearrange this. If I had done W first, and then V, my picture would look like this. And the result would be down here, and you can see that the result in the other order is actually the very same as the result in the first order. Okay, so that's what it means to be commutative. Okay, vector addition is associative. So again, this is a familiar property from real numbers. What this means is that when you write sums of vectors, you don't actually need parentheses, because you don't have to worry about the groupings. You don't have to worry about which one you do first. So instead of this parenthesis, I could actually just write, V plus W plus U. And I don't need any parentheses. Okay, there is a zero vector such that you add the zero vector to any vector that's the same as vector. Okay, and so that's again similar to the real numbers. Every vector has an additive inverse W such that V plus W equals 0. Of course, what's going on here is that if V is a vector, which you represent by arrow pointing in that direction, then W in this case would actually be negative V, would be an arrow pointing in exactly the opposite direction. So if I draw an arrow pointing in exactly the opposite direction. And you know that if I add these two vectors by head to tail, then I go up the first and back the second, and I end up at my starting point. The sum of these two vectors is actually the zero vector, which I can represent as a point. The set V is closed under scalar multiplication. Right? So notice that multiplication involves two different types of objects. It involves a scalar, which is an ordinary real number, times the vector. And scalar is very descriptive, because what a scalar does is it scales the vector. Right? If I have a vector and I multiply it by 2, that means I'm scaling it up by a factor of 2. If I multiply by a half, I'm scaling it down by a factor of 1/2. If I multiply it by -1, I'm scaling it in the opposite direction. Addition of scalars distributes over scalar multiplication. Okay, so if I add two scalars and multiply by a vector, that's the same as multiplying the vector by the first scalar and adding the same multiple of the second scalar. Now you can draw a picture to show what what this means. If you think of vectors in terms of arrows, this makes a lot of sense. All right, and there are two distributive properties, distributing over multiplication and over vectors. Okay, again, you can draw pictures to illustrate this. And here we have associative with scalar multiplication. Now, in a way, this is, yeah, okay, no, this is fine. All right, so we can multiply the scalars first and then multiply by the vector, or we can take the scalar and multiply by the vector. Now, for those of you who are familiar with dot product, this is not the dot product. This is ordinary multiplication here. These are not dot products. Dot products involve two vectors. So this is ordinary multiplication, or I should say scalar multiplication. Sorry, this is scalar multiplication of a vector with a scalar, not dot product. Okay. So multiplication by the scalar 1 is the identity. If I scale a vector by the unit, then I get the same vector back again. Okay, so that's a complete list of properties for vector space. You can see that these are similar properties to real numbers, only it's a little more complicated because you have two types of objects. You have vectors and scalars. And you can say the additive properties are like the additive properties of real numbers. And the multiplicative properties with scalars are similar to multiplicative properties with real numbers. All right, so here's one example. Let's consider a set of row vectors consisting of all multiples of 1, 2. Now, of course, we know that 1, 2 is an example of a vector, and actually R1, 2 is in the vector space, which we can call R2, the set of all two-dimensional vectors. But now we're looking at a subset of R2. We're looking at all two-dimensional vectors that have this form, A and 2A. You can put a comma in between. Okay. So here's some examples of members of V. Unfortunately, this is not correct. 4, 6 is not in this set, because you would have to have 4, 8 to be in the set. This is certainly true. 1/2 and 1, that's in the set. Minus 100, minus 200 is in the set. And 0, 0 is also in the set, because all of these vectors have this form. All right, so again, this is not in there. This V is a vector space under the natural addition. So if I add these two vectors, I'm going to get this result, because you add vectors component by component. And notice that this can be written as A1 plus A2, comma, 2 times A1 plus A2. Okay, so this sum of vectors that both have this form also has the same form, that the second component is twice the first. Now if I multiply any vector of this form A2A by R, then this is still true. The second component is twice the first. Okay. Okay. Now what we have actually shown is closure. We've shown that two vectors that have this form still have the same form, and we've shown closure under scalar multiplication because the R times a vector of this form still has this form. There are other conditions also that need to be satisfied, so we're going to go through and verify these carefully just to see how they work. Whoops, that's not what I needed. Okay. All right, so we will first check closure. Now this is just a recap of what I already mentioned. If you take two vectors of the form that are in the space, that the first component times 2 is the second component, you add them together, and you get that the sum also has the same property. Okay, so if you have to write out a proof of closure, the proof of closure will look similar to this. Of course, if you have to write proof of closure, you'll have vector spaces of different form, but the outline of the proof, the idea of the proof, is the same. Okay. We can also prove commutativity of addition. And the way you do this is show by an example that uses unknowns. Of course, you can't do an example using particular numbers. If I just said that 1, 2 plus 2, 4 is equal to 3, 6, that's not enough to show in general. But if I indicate a general element of V by V1 to V1 or W1 to W1, then the proof that I come up with is a general proof, because I can make this equal to any element of V. So here we have commutativity of addition. Same idea. Show that it works for any vector of the form W to V1, V1 to V1, or W1 to W1. Okay. Associativity, the idea is the same. You take V plus W plus U and express it in component form. And since both components are associative, then the result is associative. In other words, this vector here can be thought of as first component, comma, second component. This vector here in different order can be thought of first component, comma, second component. These two components are equal because of associativity of real numbers, and these two components are equal because of associativity of real numbers. Because the components are equal, the two vectors are equal, and we're done with the proof. Okay. For condition 4, all right, this one is just, condition 4 means that there is a zero vector that when summed to any other vector gives the same vector. So we can exhibit explicitly a zero vector that's in the set V and show that if we add this to any vector in V, we get the same vector back again. Okay. Condition 5, existence of additive inverse. In the same way, if we take an arbitrary element of V, we can construct this vector. Now notice that this vector is in V also, because the second component is twice the first. And then we show explicitly that V plus W equals 0. So W satisfies the condition of inverse, so W is the inverse of V. Okay. Now there are 5 conditions that talk about scalar multiplication. Right? And this, I think I'm just going to let you read these proofs, because the philosophy is just the same. You take an arbitrary element of V in this form, and then you perform the operation and show that it satisfies the required property. So you can prove closure, you can prove distributive property, and distributive property of addition, and the associative property of scalar multiplication in exactly the same way. All right, so you can read those in the chapter, or it's probably enough just to read them on the slides if you like. Okay, and here's the same thing for identity. You verify with a general form of a vector in V. Okay. Since the set V satisfies all the necessary properties, the set V is a vector space. Now this is actually called, we know that this set V is a subset of R2, and I think we'll come up with this definition a little bit later. V is in fact a subspace of R2. Right, now, another example, the set R3 is a vector space under the usual vector addition and scalar multiplication operations. Okay. And I'm going to skip through this very quickly because it is, you're doing the very same things. You're representing arbitrary elements of R3 in terms of representation like V1, V2, V3, or W1, W2, W3. And you're verifying that any vector in this form satisfies the necessary conditions. So we have closure, and closure of and commutative, and associative, and zero vector, and additive inverse, and closure under multiplication. And this was distributivity of scalar multiplication. This is distributivity of vector addition. And this is associative scalar multiplication. And this one is unit multiplications, scalar multiplication by 1. Right, so those were the 10 properties, and you can spend a little more time on that if you want to see that in fact R3 is a vector space. Okay. All right, here's another example that's a little more different from what you're used to. Consider the set of all polynomials. In this case, the polynomial has degree 2 or less, because these numbers A are real numbers. They could possibly be 0. So think of all the possible quadratic polynomials, and this polynomial is a vector space under the usual operations of polynomial addition. Right. Now, you can actually think of this polynomial. There's the constant term, there's the term that multiplies x, and there's the term that multiplies x squared. Now, when you're adding polynomials or multiplying by a real number, these three terms add as placeholders. I always add constant terms, I always add terms multiplied by x, and I always add terms multiplied by x squared. These terms don't mix. Now remember, we're not looking at polynomial multiplication. We're only looking at polynomial addition. Polynomial addition and multiplication by scalars. If you just restrict yourself to those operations, the set of polynomials is a vector space. Okay? And you can follow through again these examples. This is usual polynomial addition. This is how you define polynomial scalar multiplication. We can always take a linear combination of polynomials up to degree 2 and get another polynomial of degree 2. Okay. All right, here's another example, the set of 3 by 3 matrices. All right. In fact, you can think of this as a 9-dimensional vector, because when you add matrices, it's the components that add together without interacting again with each other. So you could almost think of this as a 9-dimensional vector just shaped differently. Again, at this point, we're not talking about matrix multiplication. We're only talking about matrix addition and scalar multiplication. So if we restrict ourselves to these two operations, the set of 3 by 3 matrices is a vector space. The empty set is not a vector space, so this is just some small bookkeeping. However, so the empty set is not a vector space, but this is a vector space. You can verify all the properties. So this one element vector space is called a trivial space. This is the kind of thing that mathematicians worry about, but in practice you don't really need to worry too much about this. Okay. All right, so let's prove some properties of vector spaces. Okay. In any vector space V, for any vector in V and any real number, we have that 0 times V is 0, minus 1 times V is the additive inverse of V, and R times the 0 vector is 0. So we can actually prove these from properties that we've already proven. Now these are things that you intuitively think should be true. If you scale a vector by 0, it should shrink the vector down to 0. If you multiply a vector by minus 1, that is, you're scaling it in the opposite direction, it should give you the additive inverse. And if you scale the 0 vector, it should remain 0 vector. So this agrees with our intuitive ideas of vectors as arrows, but we can give a formal mathematical proof in terms of the properties that we've seen before. So let's go ahead with a proof of this lemma. Now, I want to go through this a little more carefully to show how all of these steps do follow from the properties that we described. Now this first one, we want to show 0 times V is equal to 0. So somehow we want to split out the 0 times V and get it equal to 0. So This is a way that you might not have thought of, but follow through this and see if you can follow the argument. Now, I can write v as 1 plus 0 times v. Now, what property is that? Go back here and see. I'm just using this property that, property 10, you see? That I can write v as 1 times v. And the fact that I can write 1 plus 0 as 1, that's just ordinary facts about real numbers. So here, I've actually used property 10. So I'm going to indicate that. Okay. Usually you write these equalities one after the other, but he's not giving me room here, so I'm just going to say that this equality follows from property 10. Okay. Now, how did he get from here to here? If you look at the properties, he's actually distributing the scalar addition. So let's see how that, what property that is. That's this property 7, where you have scalar addition and you're distributing over a vector. So that second equality here follows from property 7. And now he's talking about additive inverse. He's adding the vector w to both sides. Now, there's no explicit property in the list that says you can do that. You can just call that substitution. Since v equals v plus 0 times v, we're just substituting v with v plus 0 times v. So I can call this substitution. Now, how did he get 0 over on this side? Well, he said w plus v is equal to 0. That's the property of additive inverse. That was property 5, if you see there. So he's using property 5. And he did that on the left and on the right. So here he actually used the associative property. I mentioned that the associative property means you don't need to write parentheses when you do a series of pluses. So he's actually using 5 and the associative property. So let me note that down too. That's property 3. Now finally, how does he get from here to here? He gets rid of the 0 here because the 0 vector plus any vector is that vector. So here he's using property 4. All right, that seems like a long, involved way of proving something that seems like it should be obvious. But remember, you have to use the properties that we've assumed in order to prove the properties. You can't just use your intuitive idea about vectors, because as we've seen, there are some vectors that don't really fit with our intuition. You wouldn't intuitively think of polynomials as vectors, and we want to prove things that are general for any possible types of vectors. Okay, so we've proven part 1 of the lemma, that 0 times v is equal to the 0 vector. And we're going to use that in the other two parts of the lemma. Okay, so let's go ahead and do part 2. We want to show that in fact minus 1 times v is equal to v. Now it seems pretty clear that we want to group these two together. We're going to use some kind of distributive property. So, and remember that v is equal to 1 times v. So he didn't write that here, but he's really using the fact that v is 1 times v, and then he's using the distributive property. So we're actually using two properties here. We're using the fact that v equals 1 times v, so we're using 10. And we're also using this fact that we can distribute addition over scalar multiplication. So we're using 10 and 7 here. Now once we've gotten here, this to say minus 1 plus 1 times v, that's just arithmetic. So that's just this one's just arithmetic. Now once we have 0 times v, how can we conclude that 0 times v is the 0 vector? Well, that's part 1 of the lemma. Okay, so I'll just call that L1. So we're using what we just proved to establish the result. So now we know that to get an additive inverse of a vector, you just multiply it by -1. And that's true in any vector space. How about for part 3? R times 0 equals 0. Well, let's do some similar type of trick. R times 0 is equal to R times 0 times 0. So let's see how he got this one. Let's see what property enables us to do that. Okay, well actually it's not a property here. What we're using is lemma 1 again. Lemma 1 says that 0 times any vector is equal to 0. So in particular, 0 times the 0 vector is equal to 0. So this equality follows from lemma 1. This equality here follows from lemma 1. Okay. Now from here to here, we're just using associative property of multiplication. That's property 9. Okay. So we are just using the properties that we have proven already. Okay. All right, now we want to talk about subspaces. I'm going to make that into a separate video.